Okay, so I think we can start. So although this is second lecture, this is technically lecture 1. The first one was like Python 0. The counter starts from 0 for me. And today we'll basically be trying to define what is generative model, because the course is called Deep Generative Model. At least the unofficial name of the course is Deep Generative Model. And my purpose for today, or rather I will be happy if by the end of today's lecture I have defined and you have understood what is the generative model. So that's the whole goal for today. One thing is that I will discuss something about the first practical. So remind me if I forget. So at the end of the lecture, I'll talk about the first practical. There is some announcement regarding that. So if I forget, please remind me. I'll talk about it at the end of today's lecture. So 1.5 hours from now, right? Okay. So we want to learn what is generative model, and we want to define what is generative model. That is our objective for today. And with that objective, let us start. Okay. So to start with, can one of you or some of you tell me what is a scientist? I mean, what does a scientist do? Have you ever thought of it? I mean, you might have thought about it, but think about a scientist. What is that a scientist is doing in most cases? Not the scientists of today's time, but think about maybe Newton, Einstein, Euler, maybe. So those famous names, right? So what or who? What is a scientist? Not who, but what? Figuring out how the natural phenomena work, figuring out how the world around us functions, right? But that is a very abstract, vague kind of definition. But what does figuring out means in this case? I mean, mechanics is one domain. Not everyone is working on mechanics, but they observe, correct? So they observe, right? Everyone agrees that a scientist first observes things, observes what is happening around us. But then what does a scientist do once it has observed? It builds hypothesis. Okay, we can agree on that. I can agree on that. Not propose, come up with a model. So we got three things, right? A scientist observes. Newton observed that the apple is falling. Some scientists observed that the sun is moving. I mean, it is actually the earth that is moving, but the observation from here is that the sun is moving. It is coming up in east, setting in west, and so on and so forth, right? So that is something a scientist observes. Everyone agrees? Based on the observation, its objective is to come up with a model. How does it come up with the model? It builds some hypothesis. And based on the hypothesis, it tests which of these hypothesis is working, holds, or which does not hold, and from that it comes with a model. So the journey of a scientist is from observation, which is data, to a model that represents whatever he or she was observing. Now, in mathematical term, or if I have to write it formally, what will it mean? If I have to write it down, it will look something like this. So, for a scientist, it has some data, right? It is observing, so it is observing data. And for our sake, let's say it is observing data in the form of xi, yi. So, it is observing phenomena, right? And it is observing throughout its life. It is using observations that others have made. And based on that, this is kind of the data it has. And based on this data, the scientist is coming up or trying to come up with a model that gives me or that gives him or her the relation between y and x. And I will try to make it more concrete with an example all of you know. So from here, The journey is that you want to build a model or a function in this case that maps from x to y, right? Is it not the definition of supervised learning? Right? It is the definition of supervised learning. In supervised learning, you have paired data and you are trying to learn the relation between those input output pairs. I mean, label data is what we call it. And that is exactly what a scientist do. I mean, think about it. The greatest of all time, which scientist is greatest of all time? I think most of you will say Newton. Some will say probably Einstein, but most will probably say Newton, right? Newton is famous for what? Many things. He has contributed to probably all domains that we can think of. But probably the most, or one of the most at least, is the force is equal to mass time acceleration. So what did Newton observe? It observes the phenomena that if there is a body, until and unless you apply force, it is not moving. And that comes the first law of motion. The second law comes with force is equal to mass time acceleration. What is force equal to mass time acceleration? Is that not a function? Is it not a relation between force and acceleration? So was Newton not doing a machine learning model without doing a machine learning model? Or rather, Newton was proposing models that nowadays many of us are trying to build using machine learning. Right? So, for example, as I said, for example, we know force is equal to mass time acceleration, and this is all of us know about it. And this is a function. I mean, this is a function relation between force and acceleration, two vectors. This is a linear function, that's a very simple function, but it's a function at the end of the day, right? Similarly, you can think of kinetic energy is equal to half mv square. You can come up with gmm by r square. You can come up with other complicated laws also. Sometimes these laws will not be so easy, it will be in form of differential equation. But at the end of the day, what you are looking at is basically what a scientist is basically looking at is to learn the underlying function that tells us about the phenomena that is occurring around us, the physical phenomena. In this case, that is mass time acceleration, right? That is more or less the idea. Now, this idea was more formalized in machine learning setup. As I said, this is the idea of supervised learning. You have data, label data, and you are trying to find out the relation between those. If I have to take a similar example in machine learning, how will it look? Let us look into modern machine learning problems. So, in ML, one of the problems that I can at least think of is taking your input X in this case is maybe some pictures, your image of your face, and your output is, let's say, emotion. You are sad, happy, worried, nothing, and all of those things can happen, right? So, you can imagine that in ML, your input can be an image, and what you're trying to find out is probably emotion. Right? You can also think about, okay, I can make it simple. I have images of dog and cat. You can find out whether it is a dog or cat. The most popular canonical example that is in existence in machine learning, right? That you can think of. Now, if you look into these functions, be it a neural network or whatever, a network or a machine learning model, uh, or a physics-based model like the force is equal to mass times acceleration, these are all deterministic model. This model, be it this model or the usual model, Both of these are deterministic. Now, when I say these are deterministic, what do I mean? What I mean is that if you give a input, which is, let's say, acceleration, you will get a unique force, F. It will not happen that you are giving one acceleration and there can be multiple force that is possible, right? That will not happen, and that will not happen if the mapping that we are learning, if this M, this we are learning is deterministic, right? But real world is not so kind. The data you will be having will have noise. Data is never noise free. Whatever data you have, that might be, I mean, whatever model we assume to start with, that model might not be perfect. So, in a real world setup, whatever model or whatever data you are working with, those are not exact. The data is noisy, the model is based on certain assumptions and approximations, right? And so, what is necessary is to quantify the uncertainty in your model because of noise in your data and because of the fact that your model that you have assumed, let's just say you have assumed a machine learning model, some summation of alpha I xi to the power p, let's say, or a neural network model. I mean, that is an assumption. No matter what model you assume, you are selecting what basis function to use, and you are selecting how many basis function to use, and all of those things you are assuming. So, as a result, there is some uncertainty in that also. So, in real world, my data is noisy, and we often make assumption about the model. Now, if there is someone who have not done a machine learning course and is sitting in this for the first time, when I say you are making assumption about the model, think of it like a curve fitting in Excel. When you have data you are trying to curve fit, you say that do a exponential fit, do a linear fit, do a polynomial fit. That is a choice you are making, and that's where the assumption is coming. If you have not done machine learning, think of it like curve fitting in Excel. That all of you have done, right? In curve fitting, you decide whether you want to do a exponential fit, a polynomial fit, whatever, right? You decide that. That's what I'm talking about when I write that we often make assumption about the underlying model, right? Sorry. Okay. And because of this, uncertainty is introduced in your system, right? Because of this, uncertainty is introduced. Okay. There is one more reason you might want to make your model uncertain, and that is to make it creative. I'll not explain this, I'll just saying it now. I'll explain it maybe much later in the course. But you can make your model uncertain to allow it to be creative. If it was a RL course, I would have said to make it or to help you to exploration. In that case, I would have said that. But in this case, I will say to make it creative. That is one more possibility why you will want your model to be uncertain. And in practice, you are fine, right? Suppose you want to predict whether tomorrow there will be rain or not, or what will be the temperature tomorrow, let's say. And if you are getting a prediction which is probabilistic, let's say it is saying tomorrow the minimum temperature will be 5 degrees Celsius with 85% probability. You and we in general are fine with that. we don't say that we cannot trust it. Yes, if it is 50% probability, then we will not trust it. So that means it can go either way. But 85, 70, 90%, those are numbers that we can trust, and that is what you see on your mobile. When you see whether tomorrow there will be rain or not, you see a percentage also there along with that. So those models are probabilistic. When you use ChatGPT now, you do not get the same result for the same question you ask. You see a variation. Those models are probabilistic. Most models are probabilistic. Only a few are not. Most machine learning models are probabilistic one way or the other, right? And those models are made probabilistic by design, sometime to account for these uncertainties, to allow it to capture these uncertainties, and sometimes to make it more creative. Okay. Okay. So now if we have to introduce uncertainty, what do we need? What tool we need? Exactly, we need probability. So whatever I was talking about for last 20 minutes, 15 minutes was to motivate the need of probability in machine learning. All of this story was to motivate that why you need probability theory, why you need a tool called probability theory in machine learning, not even generative model, but machine learning for now. Okay, so this means to model it, we need probability theory to model it. It is clear why we need probability theory to model it? Any doubt on the necessity of probability theory in machine learning in general? Because the course is called probabilistic machine learning, so I wanted to first motivate the need of probability. Is there any doubt on that? By the way, how many of you are doing the uncertainty quantification course? There are few, right? So I think why uncertainty is needed has already been covered in that course, for you at least, right? That course must have covered it in quite some details. Why uncertainty is important, and it might have also started talking about probability already. Okay. So yeah, I will ask one more time. Is there any doubt or any general questions, queries on the part that we discussed till now? I mean, this is quite obvious actually. Most of you already know it, but I wanted to start with this thing because that makes it simple to now go into probability theory rather than directly starting with probability theory. This is fine? Okay. Okay. So if this is fine, we can now go to the next part of today's lecture. The ultimate goal is to define generative model. Keep that in mind. So the next part is about probability theory, some fundamental review of probability theory, most of which I hope you already know. So it will be very quick, but basically talk about certain aspects of probability uh, theory, right? So review of probability theory. Now, any probability theory book you take, it can start with one or the other thing. If it is more mathematically involved, it will in many cases go to directly the probability space, and it will try to define what is the probability space, and it will talk in that. In the probability space, everything will occur, right? I will also go to probability space. But to beat probability space or a very basic book on probability and statistics, the first thing you get is set theory, but even before set theory, random experiment. Everything starts with a random experiment. Set comes to tell you about the outcome of the random experiment. But first, there is a random experiment. That is the first thing in any probability theory book you take, right? So, the first thing is random experiment. What is a random experiment? The name itself says what is a random experiment? Yeah, I should not use the term random to define something that is having random, but an experiment whose outcome is cannot be predicted with certainty, right? I mean, another way of saying the outcome is random. So random experiment is any experiment, the outcome of which you cannot predict with certainty, right? So it's an experiment whose outcome can't be predicted with certainty. Example, coin tossing, the obvious example all of us are aware of. Coin tossing is a random experiment. If you toss a coin, you cannot predict beforehand whether it will be head or tail, but you know it will be either head or tail, right? So example, coin tossing. Right? Coin tossing, dice throwing, and there are many other things, but these two are the obvious ones. Even who has not done any probability course will understand that these two you cannot predict. When you throw a dice, you do not know it is 1, 2, 3, 6, whatever, right? When you toss a coin, I mean, you do not know head or tail, right? Second thing, after random experiment, what is the next thing? Sample space, right? What is the sample space? All possible outcomes, right? This is having all possible outcomes, which means if I take the coin tossing example, it will be something like sample space, it is head and tail. There can be nothing else. It will be either head or tail, right? That is the sample space. Okay. Now, something that, let's see if you know it or not, but something little bit different from what you usually do after this. Okay. Let's take an example. Okay. Let's say I have a random variable, not a random variable, a random variable I have not yet defined. So let's say there is a random event, okay, random experiment that I am doing, which gives me output as x. So a random experiment which gives me, let's say, numbers. Okay. Okay. So I have x which belongs to some real space. Okay, real number, negative, positive, all of that is possible. From this x, I take two subsets A and A1 and A2 of R. Okay. Subset A1 is 0, 2, right? It means subset A1 is basically x can take any value, any real value. Subset A1 is all those values of x that can be there between 0 and 2, right? There is one more subset, let's say A2, which is 15 and I don't know 20. Do you understand why A1 and A2 are subsets of R? R means x can take any real number, negative, positive does not matter. A1, it will take any number in the range 0 to 2, in between 0 to 2. A2 will take any number, real number between 15 to 20, including 15 and 20. That's what the square bracket means, right? You can have two sets like this. Now, if I ask you a question, how can we compare these two subsets? Is there some way we can compare these two subsets and comment on them? Let's say, for example, can you comment on which one is bigger? Which subset is bigger? If I ask you this question, can you comment on how we can do that? Hmm? Any idea how we can say which subset is bigger, which is smaller? Range is 0 to 2, 15 to 20. What does it say? We can uh, and what will that give me? But A1 has, what happened? A1 has infinite numbers because it can take any real number between 0 to 2. A2 can take any real number between 15 and 20. So we are looking at infinite possibilities here. But how will that tell me anything about the subsets? I'm not interested in the numbers inside the subsets. One and one will say how a number within the subset A1 is related to some other number within A2, right? But it will not say which subset is bigger. One by one. So someone is saying from there, yeah. We can map it to a number and then comment it based on that number. What is that number called? That's correct. But what is that number called? You were saying something in the mean. I mean, how will you map to natural numbers and why should that matter to me? And how do you know your mapping will be the only mapping that is possible? One can, you're louder. There is no subset is infinite. It can be 0.1, 0.0001, 0.00001, and you go on like that. So that possibility does not exist. The cardinality is infinite. Norm on that, he said measure. So I'm coming to both, right? Both are in the right direction. So basically, both of you, what you are saying is that we can define a scalar quantity that represents the subset. You said norm, which is a scalar quantity. You set a measure, which is highest minus lowest, which is a measure. And the terminology is what I just used, measure. We define a measure for the subset, and by based on that measure, we can decide which one is bigger or smaller. For example, there is something known as line measure. In line measure, what you do? You do that two bounds, subtract them, take the mod of that. So, for example, if I do that, what is the measure of A1? Line measure 2. What is the line measure of A2? 5. Which one is bigger? A2 is greater than A1. Louder. You can, but that is not a measure. For example, it is possible that one is 0 to 2, or let's say one is 10 to 12, the other one is 0 to 10. In that case, that will be problematic. Exactly, but why should that matter? Why should that only the maximum matter and not the minimum? It is one quantity of that. It is one quantity of that set, which is the supremum or the maximum, the higher upper bound. But why only the upper bound matter, and why is it the upper bound that is representative of everything? For example, if I have to represent this class, it will be the number of students. It should not be who has the highest CGPA. The highest CGPA should not represent the class. I mean, something like that. Can it be a representation? Yes, someone can take it. That's fine. But is that a good representation? In most cases, no. I mean, one of the answer I also get is mean and compare the mean and all of those things. That's also a common answer. But what I want to focus on, and that will be needed, is measure. In this case, it's a line measure. So that means you take a real number line, calculate the length, line or length measure. Length is the correct term. Okay. calculate the length of these two things, and based on the length you decide which one is bigger or smaller. What will happen if it is in R2? It will become area measure. If it is in R3, RD hypervolume. Hypervolume. So anything more than 3 dimension we cannot imagine. So it's a hypervolume. So this is how you generally do it. It has a name, by the way. This length, area, and hypervolume. This all comes under these are all in the Euclidean space, right? So it is some complicated name. Starts with L. I have forgotten. Yeah. Yes. That is one, but the spelling is even more complicated. I will not write it. Okay. It has some GUE and something is sitting at the end. I think LABESGUE, something like that. But the pronunciation is LABESGUE, yeah, something like that. Anyway, but it's basically, I call it basically, it's in Euclidean space. Anything in Euclidean space, you can use this measure, which includes this length, area, and volume to represent that. Okay. So that is the measure. But by the way, this is not the only measure. You can come up with your own measure. Measures would have 2-3 properties, and that's all. What are the properties? That measure of any thing that you take should be a positive quantity. Measure of a null set should be 0. Or usual properties like that. And measure of two subsets would be equal to measure of first subset plus the measure of second subset. So there are 3 properties of this length, area, and volume measure. The first one is that measure, let's call it mu, measure of any set is greater than equal to 0. Okay, measure of any set is equal to greater than equal to 0. Second one is measure of a null set is equal to 0. Third one is measure of two subsets is equal to, or measure of sum of two subsets is or union of two subsets is equal to measure of the first subset plus measure of the second subset. These are the 3 properties that it has to satisfy. Now you come up with any measure you want and you name it after yourself, and that's fine. Okay. If your name is X, you call it X measure, and that's fine. Okay. This is creating issue today, but that's okay. Okay. We need it to be non-negative because generally when you measure these things, right? Let's say I call it length, right? Length cannot be negative. Area cannot be negative. Volume cannot be negative. So in that sense, right? So in that, from there it is coming. Okay. So mean is generally not a measure. Mean is, I said many people answered that we will compare the mean. Because he was saying the supremum, I said many will also say they will compare the mean. But even mean is not a proper measure, it will not satisfy those criteria. Measure has to satisfy those criteria, right? So let us write it down, whatever I was saying. Oh, I lost my pen, I cannot locate my pen. Ah, got it. Okay. So to compare two subsets, we use measure. And mu is a common terminology used for measure. I mean, mu later will probably use for mean or expectation, but for now let's call it measure. And any measure, I mean, at least the line, the length, volume, and area measures, for example. So properties of measure, properties of measure, and for the matter of fact, for all measures actually, is that mu of A, where A is a subset of real space, right, is greater than equal to 0. This is the first property talk about. Mu of a null set is equal to 0, and mu of A1 union A2 is equal to mu of A1 plus mu of A2. Obviously, A1 and A2 are disjoint, obviously. They have nothing, no intersection. Right. Okay. This is the measure that we can define any, and it need not be probability. It is in Euclidean space. There is nothing probability about this, right? X is a real, belongs to the real space. You have taken two subsets from there without defining any probability. So there is nothing probabilistic about it. And use that. If you have to compare them, the common thing is to do or use measure. If you have to build the intuition of measure, I will say that when I say measure, think about length, area, volume. That's why I'm using those names. Those are not standard names. I'm using those names even though those are standard not standard names, because those will help you build a intuition. If I just use measure, it will become very abstract. Okay. And probably after today's lecture, we will not even use measure. But we want to use measure to reach some point, and from that point, everything will be based on that, whatever that is. Okay, we'll see. For hmm. Why? That is intersection, right? I said when there is no, they are disjoint. I mentioned that when A1 and A2 are disjoint subsets, then okay. And you know, in case of what you were saying, what will happen, there will be a minus sign come. And you know all of this from probability. You can understand that where I'm going with this. Anyone who has done a probability can see where I'm going with this, right? I'm not talked anything about probability, but this is measure. But you can see that all of this holds for probability also, and I'm going there only next. And because I mentioned it, why am I talking about this? Because you have to remember, like X belongs to R, which is some real, right? In probability, what do we have? No. Sample space. All possible outcomes are there in the, all possible value X can take are in the real Euclidean space. All possible value X can take is in the Euclidean space. All possible outcome of a random experiment is in the sample space. So R is equivalent to sigma, capital sigma in this case. Clear? Why it is sigma and not 0, 1, anything? 0, 1, I have not even come to that. So in probability theory, we have sigma, right? Which is the sample space. It's already defined somewhere, I think. Yeah, here, right? And from sigma, you can create different possible subsets of sigma. Like if it is tossing a different coin, it can be head, 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 tail, and all of those things, right? You can create. You can always create from here. You can create F, right? Sigma is having all possible outcomes, head and tail. F can be only head. That's a very simple example. It will become much more complex if it is 10 time tossing a coin or tossing 10 coins simultaneously. It will be head, tail, tail, head, all of those things will come, right? It should also include, like if I toss a coin 3 times, what is the, or throw a dice, what is the chance that the average will be 2, 3, all of those things will come in F, right? F has a name, I will not take that name, but F has a name, okay? Those who are doing uncertainty, this name probably has been covered there. So you can create a subset like this, and then for that F, from that F also you can come up with a subset of F, which is A1 and A2, right? So from here you can come up with all this kind of A, which is again a subset of F. You can also come up with B, a subset of F, right? And when you come up with this subset, you can now, you are now in a position to define measures in this space. You can define measure in this space. So I will repeat, because for many of you this might be new, for some of you this might be repetition, but there is no harm in listening to it twice. But for those that for whom this is new, I think it is important that you once you follow it. So in the x, when I was giving, there was a real space. It means x could take any number that is real. Similarly, if I go to the probability theory, I have a similar thing which is my sample space. All possible outcomes are there in the sample space. From the sample space, I can always bring out a subset F, which has all possible things of those things, right? And from that, I can create subsets now, A, B, and all of those. You can see how subsets can come even in the probability theory. And if subsets come, to compare those subsets, what do we need? Measure. What measure we have here is the probability measure. Because we are doing it for probability theory, we have a probability measure. So here we define, we compare A and B using P, which is known as the probability measure. This is little abstract, but it will become very clear in a short while. Okay. So let's take the simplest possible example, which is tossing a coin. What is sigma? Head and tail. A and B can be, one can be head, one can be tail. I have to compare the event of or subset in this case of getting a head, getting a tail. How will we compare them? By comparing the probability of getting a head and probability of getting a tail. Right? So that probability becomes my probability measure. F in this case will become a in the similar manner, but F need not be A. So if I take, let's say, throwing a dice, in that case, what are the things? It can be that getting 1, 2, 3, 4, 5, 6. These are the basic events. Then there can be getting an even, getting an odd. Then there can be getting something that is divisible by 2. 2 is okay. 3, let's say. And you can create like this, right? So F will have all of those things. Yeah. Okay. Yeah. So F has a name actually. I was not taking that number. F is known as sigma algebra. F is known as sigma algebra. Okay. This is the sample space. Then there is sigma algebra, and then there is the probability measure. And these three things together, this tuple together is known as the probability space. And probability measure is exactly same as what you do with the length or volume measure in the real space. And this will become very clear when you look into, let's say, we'll cover it later, maybe in the next lecture, but when you look into it, let's say, Gaussian distribution. Any distribution you take, think about what is sitting there at the exponential after that. That's a distance in some sense. X minus mu transpose sigma inverse. X minus, that's actually a distance. So it has direct relation with that. So you can think of probability measure to be equivalent to distance in the real space. Yes. Yes. So correct. So sample space generally only includes the why F is needed, right? Sample space only includes the basic events. For example, one head and tail, or 1, 2, 3, 4, 5, 6. Sigma algebra also contains those which are composite events of those, getting a 3 or 5 or something like that, right? Those are there in sigma, and from there you come up with this. This becomes very clear, so I will not cover it, but if you go to the slide, I will upload it. This is a roulette wheel example I have shown in this slide only. In the roulette wheel, when you look into it, you will realize what is sigma and what is F. In roulette wheel, you put money, right? You throw and based on where you are hitting, you get money. So when you hit it, you will see in the inner there is 1 to 36, but then outer there is red and black or red and blue color. And then you get money, you can bet on different things. and based on the probability, the money you get changes. Okay. So that is the reason. So the fundamental things are in the sigma, the basic outcomes, but the composite ones are not there. So that is the reason. Okay. What is P? Oh, create. Create is a wrong terminology. I mean, you can have. I mean, have is probably the correct terminology. I mean, you don't need to create. It already has it. Okay. That's. I mean, you can imagine is what probably the correct term. Hmm. You will, yes, you will look into it. Sample space does not have a sample space. Generally, is sigma generally contains the fundamental outcomes. Okay, like in tossing a coin, you get head and tail, 0 and 1, something like that, right? So it does not actually. F has all the, because those things are created based on those fundamental things. In that sense, you can create even more. So, but whatever is there is based on those fundamentals. So in that sense, right? Okay. Now, probability measure is a measure. It holds the exact same property with a small change. What is that change? So this were the properties in probability measure. Which property do you think will change? 0 to 1. The first one will not be greater than equal to 0. It will be between 0 and 1. The second one, null set probability is 0. You know that. And A1 union A2, if their disjoint is equal to probability of A1 plus A2. You know that. But these three are the Kolmogorov hypothesis actually, if you look into it. Kolmogorov axioms, right? That comes from the probability measure or comes from the measure theory. Okay. So probability, the properties of this are probability of A, this is 0 less than equal to less than equal to, okay. Then probability measure of a null set is 0, and if there are two disjoint events, then it's probability of A plus probability of B. Okay, we are just defining some bare minimum definition that we will need for this course. Okay, these are the bare minimum definition, and by doing all of this, I am trying to reach two things. One is random variable, the other is PDF and CDF. That is what I need, and those things I want to put it on a sound footing. So those things actually comes from this probability measure. That's why I want to define what is probability measure. After today, I will never use this terminology probability measure. I will use only PDF and CDF. But this probability measure is important because you should know where this PDF and CDF are originating from. If you do a proper statistics course, the whole course will be on this measure and all of those things, right? But we don't really need those terminologies and theorems and all of those things. Our focus is on machine learning, our focus is on probabilistic machine learning, our focus is on generative model. You have a question? Hmm. Yes, you can think of it like that. A is the element of it. You're right. You're right. You're right. A is the element of it. Correct. Because it has all the subsets. You are right. Exactly. Thank you. So it's an element actually. Okay. I'm not correcting it, but you please note it down. It's an element. Like from there, all the possible, and each of those are correct. Thank you. In some sense, not the power set exactly, but it's all set of subsets, as you correctly pointed out. Right. Like whatever you can, the combination you can think. So roll-it wheel. Actually, I like that example. I covered it once last time, but today, yes. All possible things, yes. And yes. Okay. Okay. So we have what? We have probability measure. Probability space, simple. These three together is known as probability space. These three things together is defined as probability space. What is this utility? It's recording, so I'll not tell it. I'll tell it sometime. It's a joke, but I'll not make that joke on camera. Okay. So, but yeah, it generally in most cases you will not need it. You will directly work with PDF, CDF, and random variable. Okay. So finally, almost finally, I'll say, let us come to random variable. Okay. Once we come to random variable and PDF, we are in a position to define generative model. That is the objective. Keep that in mind. I want to define generative model. I'm doing all of this, discussing all of this to define that. This is my probability space. Okay. Now, so this is my probability space, but this sample space, right? Let's talk about this sample space a little bit more. How does a sample space looks like? Coin tossing, how will it look like? Head and tail, right? But in reality, in many of the cases, what you observe is actually not the event directly. What you observe is some measurement which is function of this event. Let me give an example. Suppose I give you images. Images, one image per person, or one images of dogs, let's say. What will you measure? What are you seeing? Image, right? But what you are registering in the computer is numbers, pixels. Because computer will understand number. Similarly, head is what the outcome of a coin toss is. That's probably what we will register in computer is 1. Tail is also a outcome, but what will register is probably 0. So what you are actually working with is some not measurement is because you will confuse it with measurement. Let's say observation. You are working with observation, which is function of the elements of sample space. Your element of the sample space is head and tail. Your observation is 0 and 1 or 1 and 0. Your element is images. Your observation is pixel values RGB, DRGB, image, so RGB 0 to 255. That's what you observe. So from here, what do you understand? There is something that we need which should map the elements of a sample space to some real number. This real number can be a scalar, like head to 1. The real number can be a vector. The real number can be a matrix. It can be a tensor also. What is this mapping called? Random variable. It is neither a variable nor random, but we call it random variable. The mapping is deterministic. Head means 1. There is nothing random there. And it's a function. It's not a variable. So it is neither random nor variable, but this mapping, this function is known as random variable. So we have a x, right, which maps this to this. Now I am writing R, but this can be RD as well, d dimensional vector, right? It can be RD cross P as well, a matrix. But I am writing R for simplicity. Think about head and tail. So example is, if this is head, this is 1. If this is tail, this is 0. And this x is known as the, as I said, random. So what is the definition of random variable? A random variable is a function. A variable is a function. Seems odd, but it is A random variable is a function that maps elements in the sample space to some real number, or that maps the sample space to the real number. That is a random variable. Okay, clear? Any doubt? This probably you knew already. But now think about it. So random variable, let me write down the definition. Random variable is a function that maps sample space to real number, right? It maps sample space to real number. But what did we have with sample space? There was something that was associated with sample space. Along with sigma, there was something in the probability, it's written, right? There is a probability measure that is associated with sigma, right? What will happen because of this? That probability measure will result in an induced measure because of this mapping. And that induced measure gives us the CDF, cumulative distribution function, also known as probability distribution function, not density distribution, right? So your probability distribution function or cumulative distribution function, the CDF, is an induced measure coming because of the definition of the random variable. Why do I call it induced measure? Because this mapping is deterministic. Your input is having a measure. Because of this deterministic mapping, you will have an equivalent measure in the map space. And that equivalent measure is your CDF. So CDF, we will talk about only CDF and PDF in this course. But this CDF and PDF actually comes from measure theory. There are very good courses on measure theories. There are very good courses in probability and statistics. If you are interested, you can go to those and study it. There are whole semester covered on only measure theory. There are semesters covered on prob and stat, multivariate statistics. The objective of this course is not that. I will not go into that, but I just wanted to take you to PDF and CDF via this measure theory. I'll repeat once more. So, in the real space, we have length, area, and volume measure, right? The equivalent of that in the probability, in probability theory, is the probability measure. We define a probability space using sigma, f, and the probability measure. So, along with sigma, probability measure is inherently associated in that space. Now, when you define a random variable that take you from that space to the real number in a deterministic way, this measure that is also there in the probability space will result in an induced measure. And that induced measure is your CDF. And from CDF, you can always go to the PDF by differentiating it, right? You can always go to from CDF to PDF through this. And it makes sense that CDF is the probability measure, not the PDF. Because PDF is not probability. CDF is probability. PDF can be greater than 1. CDF is between 0 and 1. So all of those properties you see are holds for this, right? So let me write it down. Sigma is associated with probability measure, right? Random variable x maps sigma to r. Okay. Again, I will repeat, r can be rd also. I'm writing r for simplicity, it can be r to the power d, I mean d dimensional, right? Keep that in mind. This results in induced measure CDF, and that is why each random variable is associated with a CDF, right? Any question? Any doubt? Anything you want me to repeat again in all of this? No? So let us first review what we have done till now, because there are probably some terminologies that I introduced here and there. So let us just take a moment and review what we have done till now, right? So we started with data, d xi comma yi, and I said the journey of a scientist is from data to model. So ideally you will want to learn a model given data, but your data is noisy, data is limited, your model is having some approximation. So it's a good idea to learn a probabilistic mapping. Your function need not be deterministic, you can learn a probabilistic mapping. This I mean did not made explicit, but I'm telling it now, right? And to learn a probabilistic mapping, you need probability theory. So that is why we need probability theory in this course and in machine learning in general, right? Now in probability theory, there is random experiment, all of you are aware of that. There is this notion of sample space, all of you are aware of that. And then there is this notion of probability space, which we brought in, which some of you did not know, I'm quite sure of that. Some of you knew. I mean, uncertainty, I'm not sure if this has been, if Rajdeep has reached here or not, I don't know, but he will reach here very soon. If not, he will also cover Borel, sigma algebra, and all of Borel space, all of those things which I'm not covering. Anyway, so you have this measure, length, area, volume measure, which the equivalent of which in probability theory is probability measure, and you define a probability space using a tuple, like which is your sample space, sigma algebra, and your probability measure. Now, generally we do not observe the elements of sample space, we observe some observations, which is function of the elements of sample space. And for that we introduce the notion of random variable, which is not a variable, which is not random, it's a function, a deterministic function mapping between sample space and real space. And because of this mapping, in the sample space, along with that, there is probability measure, which now becomes CDF. So CDF is a induced measure. This is more or less what we have discussed till now. So any question on this? No? Good. So if there is no question on this, there is one philosophical thing I would like to discuss before I can generate or I can go to generative model. So when you perform these experiments, right, random experiments, let's say tossing a coin, you toss a coin 10 times, you get head, tail, tail, head, head, tail, tail, something like that, right? This, what is this? Whatever you observed after tossing the coin 10 times, what is it? What? No, you observed head, tail, tail, head. What is it? You toss it 2 times, you got headed. Observation. These are your data, D, right? So I want you to build this philosophy, this view that whatever data you have is result of some random experiment someone has performed, right? If you have the MNIST data set, all of you know about MNIST, right? You have the MNIST data set. When you load some of this data set, it's like performing a random experiment. Someone have written 0 to 9 by hand, and that image you have taken, and that's what you are seeing. So those images actually realization of a random variable, right? So whatever data you have is outcome of a random experiment. This is the view you need to develop for this course. Whatever data you have is because you perform some experiment. If you go to the lab, perform 2 experiments, you get 2 data. The data are deterministic now because you have got it. But if you go and perform it 2 more times, you get 2 separate data. You have now 4 data. So what are these data? He said as good as tossing the coin. When you toss a coin, you get head. Head is deterministic, you got it already. But before tossing, you did not know whether you will get head or tail. So when you get this head, tail, head, those are outcome of your random experiment. Any data you have, you can think of it as outcome of some random experiment which you might not have performed. You have been given the data. You have only that data to work with, but it's part of much bigger data, which is some experiment someone has performed. So that is the world view. That is the philosophical view you should develop, because that will directly link to generative model. So whatever data you have, that is outcome of a random experiment. Okay. So if that is outcome of a random experiment, and with a random variable you have CDF and PDF. The objective of generative model is to learn the distribution from which the data is coming. I will repeat. I said when you perform a random experiment, you get some outcomes. So any data you have, you can imagine it to be outcomes of some random experiment, which means those data will be coming from or having some distribution. The objective of generative model is to learn that distribution so that you can sample from that distribution, which means that will allow you to generate new data from that distribution. So that's why it's called generative model. Generate is the keyword. So what you are doing, you have data. The world view is that data has come from some random experiments. So the data should be having some PDF. You try to learn that PDF. Once you learn that PDF, you sample from that PDF. If you sample from that PDF, you get additional data. That means you are generating new data. Generate. That's why it is a model that is capable of generating. So it's a generative model. Any question on this? Is the philosophy clear? How will it do it? I am not going there. That is the purpose of this course. So we will go there throughout this course. Not only today, we will talk about different ways of doing that. But the definition is clear. So any data you have is a or can be thought of as some outcome of random experiments. So if the data is outcome of random experiments, that means the data will have a distribution. So your objective is to learn that distribution either explicitly or implicitly, and learning that distribution inherently means you are now having a tool to generate new data by sampling that. Okay. The data should have that. The parameters, when I say learning a distribution, it also means that the learning the parameter of the distribution. It can. I mean it can, but ideally then it is a hierarchical distribution. And you can always integrate it out and come up with a distribution. I mean the whole idea of Bayesian is everything is probabilistic, but for this time around I'm not going into Bayesian. I'm only going into generative, but if I go into Bayesian, whatever is unknown is random. That is the Bayesian way of thinking. Whatever you don't know is random. Okay, that is the main philosophy of Bayesian. Okay, that is if you look in the previous version of this course, that's what I covered. This time I'm covering this, but that's what I covered. So yes, it can be. So when I talk about learning the distribution, again, I use the term implicit. So in most cases, you will not learn the distribution. You will learn an implicit representation of a distribution, or you will learn an implicit way to sample from the distribution. You will not actually learn the distribution in most cases. What does it mean? We'll cover it later. but it means in general to perform additional experiment. What is a sample? Let's talk about tossing a coin. The sample of it is if you toss it once, you got head. That's one sample. If you toss it again, you got it another head. So you have two samples. You toss it 10 times, you got head, tail, tail, head, 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 head. Those are 10 samples. So generating sample means performing additional experiments. Right? That is how actual samples are generated. But if you know that it follows, let's say, Bernoulli distribution, then you don't need to perform experiment. You can sample that distribution. Sampling the distribution means it will tell, for example, let's say you have a biased coin. It's a Bernoulli distribution with probability of head 0.75, probability of tail 0.25. Now, without doing any experiment, if this is known to you, you know if you perform 100 experiments, you are supposed to get 75 heads, 25 tails, more or less. So, sampling will mean that you generate head and tails in such a manner so that those probabilities are respected. So that if you are generating 1000, around 750 should be head, around 250 should be tail, without tossing the coin. You will do that because you know the distribution. That's what sampling means. Sampling means to generate the variable in such a way such that all the probabilities, proper measures are, in this case, CDFs are respected. Okay. Write it down, whatever we discussed for the last few minutes. So at least I'm able to define generative model, which was the objective for today. So our worldview is that whatever data we have as is from random experiment, right? Not necessary that the experiment is performed by you, but it is from some random experiment, right? With this worldview, the objective in generative model is to learn the distribution over data, or distribution of data. Over is not the correct term, of. The idea is to learn the distribution of the data, right? And be able to generate new samples. Okay, when you generate samples from a generative model or from a distribution, they are known as generally synthetic data, because you are not actually performing the experiments. You have somehow learned the distribution and sampling it. So those are your data, but those are synthetic data. One way of generating synthetic data. There can be other ways also, but this is one of the way, because you have performed the experiment, learned it, and then you are generating it. Those does not exist. Those are not actual experiments you have performed. They are synthetic data. Okay, that is one way of increasing your data in many cases. Okay, so to define generative model, a generative model is a model that allows you to learn the distribution over the data and also sample from the same. And when I say learn the distribution of the data, it can be either implicit or explicit. Most are implicit, one or two are explicit. Okay. Clear what is the generative model? Any doubt, anything that is not clear, please feel free to tell. The definition of generative model is clear or not. Okay. So generative model means you have data. The data has come from some random experiment, so the data is having distribution. A generative model will learn the distribution of the data. Okay. And by learning the distribution of data, it will allow you to generate new synthetic data, artificial data. We are not done with prob and stat. I'll stop here because this was the goal for today. But prob and stat, we are still remaining. We will define what is PMF, what is PDF very quickly next time. And then we'll go to transformation of distribution, which is a very fundamental block in generative model. And once we're done with that part, then we'll I'm hosting some faculty and he's giving a talk on Monday from 3:30 onwards. So I'm not available. Hmm? Thursday. Thursdays? When? Evening, right? Evening can be any day, right? After 12. So how about Thursday 2 to 4? No, class है, right? Uh-huh. 3 to 5 ही करना पड़ेगा फिर. So Thursday 3 to 5 would be okay. Yeah. Oh, मौसम कब time? हाँ, तो 3 से कर रहे हो. You can come half an hour late. That's fine. And practical anyway, so that's okay. Anyway, so that day I will probably quickly cover some basics of neural network and then give you a deep neural network, deep learning set. So the idea is as follows. In the course, we'll do generative model. While in the practical, because the first homework will come in Feb, before that, whatever two practicals we will get, that will be on deep neural network concepts, because those deep neural basic concepts will be needed for homework 1. So we'll do that. Okay. So that is basically the idea. Wednesday, second half, actually there is the institute meeting, so I'm trying to avoid that. No classes for any Wednesday. I know, but because the meetings will be there, I have to attend that meeting. But that reminds me, what about next Wednesday? That's a holiday. If I take practical on holiday, you will have no class on Wednesday, because Saturday is a working day, I think. Because this tomorrow is a working day, right? Because Wednesday is a holiday. So is it fine? Because then I can take any time on Wednesday. It will be 1.5 hours that I will take only. So is it fine? Only for this week. I mean, only for the next week. Otherwise, it will be one day. We will not change it. So Wednesday is fine. I mean, specifically those who stay outside, I will mainly ask them because they have to come. हॉस्टल वाला तो ऐसे ही आ जाएंगे, वो तो ठीक है उनको मैं काउंट नहीं कर रहा हूँ, जो बाहर रहते हैं खास करके थोड़ा दूर, उनके लिए पूछ रहा हूँ मैं. इज दैट फाइन? और anyone, yes, you stay outside, I know. Anyone has any problem with Wednesday? Right? So let me figure out. I mean, 2 दिन हम decide करते हैं. One was Thursday 3 to 5. The other is Wednesday second half. ठीक है? Because Wednesday, whether they will allow me to book the room or not is a different story out of its own. So I'll email you after checking whether they are allowing me to book rooms on Wednesday or not. If they don't allow, then Thursday 3 to 5, only for the next week. Otherwise, Wednesday. I could have cancelled it, but I cannot cancel it right now because we need this concept for your homework 1. So that's why I want to give you the practical one on as soon as possible. Let's put it that way, right? And anyways, I will not be here from 21st to 24th. I'm traveling to Singapore for those 3 days. So I think that time I will miss one lecture, which is 23rd. 23rd lecture will not happen. 20th I will take lecture, which is Tuesday. And then the next lecture will happen on 27th. 26th is holiday, obviously. Okay, so that time I will miss one class also. Okay, which I will make up later. Okay, so let us settle down on these 2 options, Wednesday and Thursday. My feeling is that they will not allow me to book on Wednesday. We'll go it Thursday, but let me try that. If I get it, I'll write an email. Okay. It will be on deep learning, basically deep learning recap kind of thing, because and basics of PyTorch and all of those things. So, okay. Okay, so thank you. Next, we are meeting on Tuesday. Tuesday 6, same location. We'll continue on probability theory. We'll wrap it up and start with generative model. Okay, hopefully we'll be able to start. Thank you.